An Atwood machine is nothing more than a pulley with a string looped around, and on one side is a larger mass, we'll call that capital M, and on the other side of the string is a smaller mass, lowercase m. They're suspended above the ground, and when you release from rest, what happens? Well, the bigger mass feels a larger force of gravity. The little mass feels a smaller force of gravity. Which one wins? The bigger mass, of course. As a result, that mass accelerates downward. And the little mass, which is connected, right, the whole system, the whole string accelerates this way. So the little mass accelerates upward. You might be inclined to call the little mass, its acceleration positive, but the big mass, you may say, is negative because this is up, this is down. That turns out not to be the correct approach, and here's the reason. They're all connected. It's the same acceleration. So if this is positive acceleration, so too must be this acceleration. And what you see is that we're making this direction the positive direction, and this direction is going to be our negative direction. That's a cool way to deal with directions. So let me write that down in the following way. This is positive, this is positive, and this is positive. Now, I drew the gravitational forces on the masses, but there's a tension force because this string that's looped around has been stretched ever so slightly by the hanging blocks. Normally, the string is a little bit shorter, like this. And so the two ends, this end of the string and this end, are being pulled back to their normal relaxed length. That means that there's a tension force right here, and there's an equal tension force at this end of the string. Notice how these arrows work out. The tension cancels some of the mg, but there's still some leftover downward force accelerating the block downward. On the other side, the littler block has a gravity force that cancels some of tension, but then there's still some force left over accelerating that one upwards. If you apply Newton's second law to this block, what do we get? Well, the second law says net force is mass times acceleration. So what's the net force on that bigger block? Gravity pulls down in the positive direction, and tension pulls this way, which is going to be our negative direction. Now, the big mass is capital M multiplied by acceleration. We do the same thing. We apply Newton's second law to this block. Just add the forces that you see in your picture. This time, tension points up, which is the positive direction, and gravity is against that. That's the negative direction. So I'll subtract the gravitational force. And then we have the mass multiplied by the exact same acceleration here as we had right there. They accelerate together because they're connected by a string. Look what happens when you add these two equations together. Add the left side with the left side, add the right side with the right side. What do we get? mg minus t plus t minus mg. Wait a second. The tensions will cancel. Let me simplify. And it just comes to this. And when I add on the right side, I have big M times acceleration plus little m times acceleration. Now we can factor out the g on the left. We can factor out the acceleration on the right. Let's make that look more like an A. And if we know how far away the big block is from the ground, We could call that distance d, or delta y. Remember that we have an equation that says the vertical displacement is the initial velocity times time plus half of the acceleration times time squared. Now, we're releasing the system from rest, so anything multiplied by 0 is 0. In place of delta y, we could put d, the distance traveled downward. And then the equation turns into this. If you isolate the acceleration, you have to multiply both sides by 2 to cancel out the 1/2. Then you have to divide both sides by t squared to cancel out the t squared. And here's what we have. Let's take that expression and plug it in right here. Okay, what's that going to turn into? Let me use a different color. G times the difference of the masses is equal to 2d over t squared times the sum of the masses. And now the final task is to isolate t squared. To isolate t squared, we have to get it out of the denominator, so I'm going to multiply both sides by t squared. Then I'm going to, in the same step, divide both sides by g, and that's going to move it over to the right. Then I've got my m plus m right here, but I want to divide both sides by m minus m, and I'm left with the expression you see here. Let me move the t squared over. And I'll move this whole expression, both of these equations, over a bit. So what do we now have? We have an equation that says if you do a bunch of experiments, so take this Atwood machine, right? And if you very, very gradually change the mass, big M, and keep little m fixed, but you just collect data with lots of different masses, big M, and in each instance, so you change big M, you let it be, I don't know, something like 55 grams, and then 60, and then 65, and 70, and so forth, and you keep changing the value, and you measure the corresponding time to fall for each mass. If you make a plot with time against mass, it should not be a straight line because there's this crazy relationship between t and big M. It's not linear. We definitely don't have something like this. That's way too simple. So we're going to have some weird shape that we don't really know what to expect yet. I think it's going to be something like this, perhaps. But how could we get a straight line? Well, look back at this equation again. What if I put on my y-axis t squared? What if I put on my x-axis the product of the masses over the difference of the masses? Now, when I rewrite this equation, I can replace t squared with y because it's on the y-axis. And I can replace that crazy fraction with x because it's on the x-axis. And if I make this plot, that does have the form of a straight line. How do I know? Because this is all a constant. I'm going to be creating an experiment where I drop always from the same distance. I measure the time it takes to fall. And when I make this graph, I should get a straight line, and it should also go through the origin. How do I know it goes through the origin? Because the equation, really, for a straight line is y equals slope x plus b. And clearly, I'm not adding anything over here. So the slope should be equal to 2d over g. And we are going to use a simulation to do this experiment. And in our simulation, I'll go ahead and tell you, the value of d is 24 centimeters. That's how high up this thing falls from. So let's take a look at the simulation. The simulation is on the website thephysicsaviary.com. We click begin, and here's our Atwood machine. Now we are going to, if we click start, it falls to the ground. Let's click reset to start again. Remember that we're keeping the little mass fixed, so I'm just going to turn this down to, I don't know, 50. You'll use a different value. Then I'm going to start out at 55, and I click start. They fall. If I scroll down to this graph, I can record how long that took. Okay, so I'm looking at the x-axis, and I say, look at this final data point right there, and then scroll down to the x-axis and figure out how much time that is. Maybe I would call that, I don't know, this is 1 point, what are those tick marks? That's 1, that's 1.1, 1.2, 1.3, 1.4, 1.5. So I probably would call this 1.01 maybe, based on where that data point is. All right, I've got my first data point. So what do? I head over to Excel. Oops, let's get a new file. Click the new button, blank document. And we will have in one column, big M in grams. And in the next column, the time, T, let's make that lowercase, in seconds. So my first data point was a mass of, I think it was 55, and the time that I recorded was 1.01 seconds. And if I'm not perfectly accurate, that's okay. Let's head back over. Or you know what, why don't I split my screen? So now I'm going to increase the mass. I hit reset, increase this big M, click start. Okay, look at the graph. What's that going to be? It's just about right on that little gray, that lighter gray tick mark. So I look down, my axis has changed. I'm going to call that 0.74. Okay, so 0.74, and that was for a mass of 60. And I keep going like this until I've collected all of my data. I'm going to collect data. I'm going to input a bunch of data. And then what I'm going to have you do is collect similar data, except that you will have as little m, you will start with 60, big M will start at 65, and you'll increase by 5 gram increments until you've collected 10 data points. So I'm going to step away, finish my data, and then come back.